Speed-time graph. When an object, perhaps a car, accelerates along a road, its speed will change as time changes. If the vehicle accelerates at a constant rate, and we know its initial speed, it is possible to use an equation to calculate the speed at any later time. Let the car start with a speed u. We call this its initial speed. Suppose it then accelerates at a constant rate, say a. Then we can let the symbol t represent the time, and let the speed at that time be v. Remember that the speed is increasing because the car is accelerating, so v will increase as t increases. The speed v depends upon the time, t. It is possible to show, using some basic laws of physics, that these quantities are related through the equation v equals u plus a times t, or v equals u plus at. Because we have assumed that the acceleration a is constant, and because the speed of the object initially, u, is a fixed quantity, then both u and a are constants. The variables in this problem are v and t. As time varies, so too does the speed of the object, because it is accelerating. If we choose different values for time t, we can use the equation to find the corresponding value for speed v. So speed v depends upon time t. The variable v is the dependent variable, and the variable t is the independent variable. As before, a consistent set of units of measurement must be used. We shall assume that time t is measured in seconds, speeds u and v are measured in meters per second, and acceleration a is measured in meters per second, or meters per second squared. A graph of v plotted against t, using the equation v equals u plus at, is a straight line graph known as a speed-time graph. Note that the coefficient of the independent variable is a, the acceleration, and the constant term on its own in the equation is u, the initial speed. Consequently, if we compare v equals u plus at with y equals mx plus c, we can tell that the slope of the graph m must be the acceleration a, and the vertical intercept of the graph must be the initial speed u. A typical speed-time graph is shown here. What does this graph tell us? Clearly, the straight line cuts the vertical axis at the point a, 0, 3. That is, the vertical intercept is 3. This means that when the time t is 0, the speed of the object, that is its initial speed, is 3 meters per second. From this we can deduce that the equation of the line must take the form v equals 3 plus at. After 3 seconds have elapsed, the speed has increased to 9 meters per second. We can see this by inspecting point B on the graph. After 5 seconds, the speed is 13 meters per second, and we can see this by inspecting point C. The speed is increasing because the car is accelerating. We can use the point B, 3,9, to find the value of A. We know that the point 3,9 must satisfy the equation v equals 3 plus at, so that when t is 3, v is 9. Substituting these values, we find 9 equals 3 plus 3a, so that 9 minus 3 equals 3a. Or 6 equals 3a. From this we can deduce that a must equal 2. We could also have deduced the value of a by noting that a unit increase in the t direction produces a corresponding increase of 2 in the v direction. Consequently, the gradient of the line, a, is 2. We deduce that the equation of the line is v equals 3 plus 2t. In this example, the gradient of the line is positive. This means the speed increases as the time increases. In some examples, the gradient could be negative, so that the speed decreases as the time increases. In such cases, the car or object will be slowing down or decelerating.